Good afternoon. So, in new synthetic reactions, today we are going to discuss about C double bond formation reactions. Those are Sapiro and Bamford Stevens, McMurray reactions, Julia lithoolefinations, and Peterson stereoselective olefinations. Right? Now, first one, Sagro reaction. So, conversion of tosyl hydrogens of carbonyl compounds having alpha hydrogen into olefin with excess of strong base organic lithium, organolithium or LDA is called as Sapiro reaction. Means conversion of alpha hydrogen in presence of excess strong base to a double bond or olefination. So this is here. So this is a LDA lithium diisopropylamine. This is the structure and tosyl groups are there, tosylates. So this is the one. And here the organic moiety that is a carbonyl compound RCOR, and this is a tosylamine group. So here you can see the substitution, and then it is converted into C double bond C R R dash. So this oxygen moiety was removed and double bond carbon is formed. So this is called Sapiro reaction or olefination, we can call it as. So C double bond O carbonyl group which is having alpha hydrogen. So this was converted into an olefin. And here solvents are ether, THF or DMU as dimethyl oxides were used. Okay. And this is tosyl hydrazone with alpha hydrogen, this moiety. And here tosyl group is substituted, tosylamine group is substituted here, right? And these are the some examples how this is tosyl group is substituted here, and this double bond came into inside here, and the nitrogen N2 and tosyl ion is eliminated, right? So same thing here, wherever the carbon is attached to nitrogen, that is a tosyl moiety. So there the adjacent carbon alpha, the alpha hydrogens, the reaction center will have the alpha hydrogens. So in between this, it will get the double bond olefin, right? In a third example, you can see the alternative, the pH C pH. So here there is no alpha hydrogens in phenyl group, so that's why it is there is no chance of any reaction in this moiety, right? And another one, the mechanism of this. So in this mechanism, you can see this substitution at tosyl amine groups, right? Amine groups are substituted here, and alkyl lithium into equimolar, and solvent has been used. So automatically the tosyl group was here and RLi is there. So lithium will go and substitute, or it will interact with the tosyl, and tosyl will be eliminated, and lithium plus with the nitrogen minus the amine diamine group is there, that amine nitrogen will be attracted towards to the lithium, right? Here automatically R minus will be available. So in next step, you can see the negative charge formation in a ring, right? And this ring will be involved in this double bond formation. So automatically this nitrogen N2 as N2 N triple bond N will be eliminated here. So automatically the molecule is in reaction medium, you have the lithium plus ion, and in ring have negative charge with the double bond. So this lithium will be substituted on negative charge. So this lithium moiety will be substituted here. So this will be reacted with, if it is reacted with the D3O plus, so D will be substituted in place of lithium. Or you can go with hydrolysis, so automatically lithium will be eliminated as LiH, and here hydrogen will come and this olefin will be substituted. If you want to go with addition, so methyl iodide, if you use the methyl iodide as a reaction medium, so you will get methyl substituted one, right? And here you can see the regio selectivity. Regio selectivity means if any compound is having two alpha hydrogens, so on which it can move, right? So majorly the 90% is here and 10% is here. So the less substituted and more substituted. So here you can see in a first position, the right side carbon adjacent to the carbonyl carbon, the right side carbon is having two hydrogens and left side carbon is having one hydrogen. So most probably, according to Markovnikov rules, the more hydrogens moiety will form the double bond group. double bond or olefination purpose. And here you can see the left side, which is less substituted one, means one alpha hydrogen is available, so it will generate the 10% of product, right? And reactions which produce unequal amount of isomers called regio selectivity. So what is regio selectivity? Means reaction which produce unequal amount of isomers. So that is called as regio selectivity, based on the number of alpha hydrogen attached to the carbonyl compound, right? And next, in case of unsymmetrical tosyl hydrogens, several reactions are regio selective, predominantly double bond orients at less substituted alpha positions. Kinetically controlled reactions in the product, less substituted olefin is the major. So here you can see the less substituted one is major ones. So these are some of the examples. You can see here which one is major, which one is minor in these two examples. And here without any additions, you can see here, right? Next one is a Bamford-Stevens reaction. So strong base is used in this reaction. It is thermodynamically controlled reaction. So conversion of tosyl hydrogens of carbonyl compounds into olefins with the strong base such as sodium ethoxide or sodamide is called as Bamford-Stevens reactions. So tosyl hydrogens with alpha hydrogens converted in presence of sodium ethoxide and solvent. So olefin formation will be there. So this is the base principal point. So this is the tosyl hydrogen with alpha hydrogen, and here you will get a plain one, and N2 is eliminated, and here tosyl is eliminated one. So in presence of different two types of solvents are available. So according to the mechanism, so if you use the protic solvent or aprotic solvent, so if it is a aprotic solvent, so benzene C6H6 or cyclohexane, so C6H12. So which one you can use based on this? So here you can see the substitution like this in a radical mechanism. If it is a aprotic solvent, that is a CH3OH or ethanol or methanol is a protic solvents. Aprotic solvents are benzene or cyclohexane. So here you can see these are the two different types of mechanisms. In one mechanism, first tosyl group is eliminated. In another mechanism, tosyl and hydrogen both will be eliminated. And here in the first aprotic solvent used, a radical type of mechanism will be available. The product is almost same. There is no difference in the product or functioning, but the difference is if you use the aprotic solvent, the radical type of functioning will be there. Means radical type of products, intermediates will form, and here you can see the ionic intermediates, right? So that is the only difference with aprotic and protic solvents, right? And what is the regio selectivity? The regio selectivity, the regio selectivity of Bamford-Stevens reaction is reverse to that of Sapiro reaction. Thermodynamically controlled reaction and gives most stable product as major. So here you can see this is the substituted, means the tosylated one. And if it is a Sapiro reaction, so major one is this one and minor one is this one. But in Bamford, it will be same, minor will be converted into major, major will be minor. So it is reverse to the Saviro reaction. Okay. So here you can see Bamford, Stevenson. So same thing. This one is in minor in Sapiro reaction, major in Bamford reaction. Here it is a major one in Sapiro reaction, and here minor one in Bamford reaction. Okay. And the next one is McMurray reaction. So this is the carbonyl group substitution in between these two carbonyls. The reductive coupling will be available. So after reductive coupling, the olefin formation will be generated. Olefin will be generated after reductive coupling. So McMurray reaction. So reductive coupling of carbonyl compounds into olefins by using titanium TiCl3 or TiCl4 with reductive agent lithium aluminum hydride or copper zinc coupled with sodium, potassium, magnesium, zinc, lithium is known as McMurray reaction. In general, in this reaction, lithium aluminum hydride or LaH with the zinc copper couple. Zinc copper couple means two metal atoms will be used as a couple, as used at a less or low temperature. Pinnacoles are obtained as byproduct competitively. So Pinnacle's will be Pinnacle's products will be available, or it will generate the Pinnacle products as byproducts. Okay. And next, solvents used as ether, THF, or DME, easy to prepare highly substituted olefins in this mechanism. So stereoselectivity is very poor in this formation of olefins, right? So titanium plus 3 Cl3 is reduced to titanium 0 as reducing agent is lithium aluminum hydride. So lithium aluminum hydride converts titanium chloride means Ti plus 3 state to Ti0. So titanium metal is produced in situ means at a time the reaction medium, whenever the reaction medium is there, in that reaction only it is developed. So titanium plus 3 to titanium plus 0 state. Okay. And next, what is the mechanism? So you can see the mechanism here. So this is a carbonyl compound. Titanium will be attached towards to oxygen electrons it will take. So automatically the carbon will the C double bond O, the double bond will attract to move towards to the oxygen, and it will get a negative charge, and carbon will get a negative means a particle as a radical, and this will be substituted on the titanium coating, right, like this. So after certain time the two carbon radicals, free radicals, carbon free radicals will be formed a bond of Cc. Then afterwards the oxygen will be eliminated from these two, and these two carbons will generate with the two radical points, and after that lastly the two carbon radicals will form a bond like olefin, means finally we get the olefins, right? This is a radical mechanism. Okay. And here you can see the most substituted one, R1, R2, R3, R4. So here you can also get the olefin by using titanium chloride and lithium aluminum hydride act as reducing agent, right? So same thing here also, you can go with the 2 moles of this aldehyde group. So here the ketone will not be interacted, the aldehyde group will interact with each other to form, because carbon is available. So because of this the C double bond O, so this will reduce to C double bond C, right? So chemoselectivity in competitive functions, if one function produce over other in a reaction called chemoselective reaction. So aldehyde is having more than ketone. Okay, right. So Julia lithogy reactions. This is also olefination. So classical reaction, and it is a modified reaction. So beta acetoxy sulfones presence of strong base gives the olefins is classical reaction. So in presence of beta acetoxy sulfones, this beta acetoxy, this is a beta position, alpha position, sulfonyl substituted position is alpha position, and the beta position with the ketoxy group, this is acetoxy group, OCOCH3 acetoxy, beta acetoxy sulfones in presence of strong base, ethanol and sodium amalgamate, sodium mercury. So in presence of this, you will get an olefin, that is a trans olefins, right? This is a classical reaction. And conversion of beta acetoxy sulfones into olefins in presence of methanol solvent is a classical Julia lithogy reaction, right? Julia lithogy reaction. This is a mechanism. You can see here SET. So here SET means a single electron transfer, means a radical type of mechanism. Single electron transfer will be there, right? So here you can see the mechanism, how and where the sodium is attacking, how it is moving the sulfonyl group, and where sodium is attacking, right? How the formation of double bond or olefin formation is taking place. Okay. Right. So this is a modified Julia lithogy reaction. So in presence of sodium methoxide, so this was done. So here you can see the RC double bonds are, right? So this is mild rearrangement here. So rearrangement will be available, rearrangement will be done here. So to form the final product. And this is a Smiles rearrangement, means intramolecular rearrangement. It is nothing but rearrangement in between, within the system, right? Here X and Y is available, and Y become in center, X become the terminal. So previously Y is in terminal, X is in internal, in between two carbons. But here it is rearranged to shuffled, means one position to another position, like this to this. It is turned. So this is a rearrangement. Okay. So same thing here also in an example, you can see the rearrangement. So after this rearrangement, you will get a product of enantiomeric, right? This is a trans product. Okay. And next one is Peterson stereo selectivity, selective olefination. So here you can see the methyl conversion of CC bond into CC double bond by treatment with lithium or magnesium derivative of silicanes or silanes and carbonyl compounds called Peterson stereo selective olefinations. So this reaction takes place via beta hydroxysilane intermediate. Beta hydroxysilane intermediate decomposes in base or acid spontaneously to form C double bond C, means CC double bond formation will be taking place. So reaction will be very fast. Decomposition of decomposition of silane beta hydroxysilane intermediates, right? And the next, this is the example you can see easily. So here the tertiary methyl trimethyl silane is available. So lithium is available here in on CH2 position, right? CH2 minus, and here lithium plus. So like this it will be generated, and finally you will get RCH double bond CHR, right? Okay. This reaction is more advantage than Wittig reaction, in which removal of PH3P triphenyl phosphine triphenyl P double bond O is difficult, right? Beta hydroxysilane intermediate is unsymmetrical, will be having diastereomerism, right? And stereochemistry of this beta hydroxysilane in basic medium undergo syn elimination, whereas in acid medium it undergoes anti-elimination. So elimination also here based on the basic medium or acidic medium. So beta hydroxysilane in basic, if it is in basic medium, syn elimination will be available. If it is in acidic medium, anti-elimination will be available, right? Next, see here in basic medium or acidic medium. So here you can see the first one in basic medium, you will get a cis group. If it is in basic acidic medium, you will get a trans one, right? So erythro, trans, major, trio, cis, major. So in acidic medium, and this is in basic medium, right?